Hello everyone, my name is Gede, and today I want to talk about my presentation about tool steel and high-speed steels. So that this is my biography. There's my name and number identification number, my lecturer, and my subject. So my presentation it references from book Metallurgy for the Non-Metallurgists by Arthur C. Reardon. First, a brief history. The modern story of tool steel began with Benjamin Huntsman, a clockmaker from Sheffield, England, who is credited with developing a crucible melting process in 1742. This process made it possible to produce cast steels with carbon level that fell between those of cast iron and wrought iron. Modern alloy. Many complex highly alloyed tool steels and highly speed steel were developed in early to 20th century following the success of the Taylor and White. These steels contain, among many other elements, relatively large amount of tungsten, molybdenum, vanadium, manganese, and chromium. These new grades enable the increasingly severe surface demands of industry to be met and provide greater dimension, control, and freedom from cracking during heat treatment than was otherwise possible at the time of their development. 11.2.1 Tool steel's properties. Attainable hardness is capability to reach a specific level of hardness through heat treatment. Individual tool steels, and high-speed steels can be heat treated to achieve a wide range of hardness values, and that often exceed the hardness capabilities of other types of heat treatable steels. Red hardness, also referred to as a hard hardness, is the capability to retain hardness at elevated temperature. Toughness is the ability to resist breakage, chipping, or cracking under impact loading. Wear resistance is the ability to resist the effect of abrasion and erosion normally encountered by contact or interaction with outside sources. 11.2.2 Grade classification. These are presently more than 40 classifications of high-speed tools and tool steel alloys according to American Iron and Steel Institute or AISI. 11.2.3 Effect of alloying elements. Carbon is Carbon is by far the most important one of the alloying elements, and it's very tightly controlled. The carbon content of many single high-speed or tool steel is usually fixed within a narrow limit, but variation within these limits can cause important change in the resulting mechanical properties and cutting capability. Silicon. Up to level of approximately 1% in influence of silicon on high speed and tool steel is relative minor. Manganese contributes to hardenability, but concentration are generally not high in high speeds or tool steel. Because relatively minor increases in these alloying elements markedly increase the brittleness of these steels and the danger of cracking upon quenching. Phosphorus has no known beneficial effect on any of the primary properties of high speed and tool steels, and is normally present as a trap element in the scrap that is used to produce these steels. Chromium is always present in high speed steels in amounts ranging from 3 to 5%. It is mainly responsible for improving the hardenability of these grades. Tungsten in high speed and tool steels is of a vital importance. It is found in all T-type steels, and in all about two of the M-type steels. or M10 and M50 are the exceptions. Molybdenum serves as the main alloying elements in the M-type grades of high-speed steel. It forms the same double carbonate with iron and carbon as tungsten, but it has roughly half of half the atomic weight of tungsten. Vanadium was the first added to high-speed and tool steel as a scavenger to remove slight impurities to reduce nitrogen levels in the melting operation. Cobalt. The main effect of the cobalt in high-speed and tool steels is to increase the red hardness, such as picture 11.1 and 11.2, which increases the cutting efficiency when high tooling temperatures are encountered in surface. Powder metallurgy tool steel. As a result of pronounced ingot segregation, conventional tool steels and high-speed steel can contain somewhat coarse, non-uniform microstructure accompanied by relatively low transverse toughness properties and carbide segregation observed in the longitudinal section or annealed M2 high-speed steel bars, says picture 11.8, illustrated the degree of segregation that is normally present in these bars and how it becomes more pronounced as the diameter of the bar increases. 11.4 Cutting tools coatings. In surf, cutting, and machining application used in industry, it is not uncommon to surface treat high-speed steels and tool steels with specialized coating to reduce frictional contact, reduce thermal conductivity, and improve wear resistance. These hard wear resistant surface coating are often used as a means of improving tools life. Important consideration when selecting a surface treatment or substrate material: coating process temperature, coating thickness, coating hardness, and the material to be machined. There are many surface treatment and treatment process that are available. So, guys, thank you for watching my video. Hope you enjoy it. Sorry for misunderstanding words. See you in the next video.